Just a quick re-recording of lecture 17 from last Monday. When I originally delivered this lecture to the internal students, there was a problem with the terminal in the lecture theatre, and it didn't actually record any of the lecture. So we're just going to go through what I covered with the internal students last week, so that you can catch up and basically have an understanding of normalization and normal forms. So we'll move on in here. Just let me start up our slideshow. So we're looking at the material from Chapter 12 of the CJD Introduction to Database Systems textbook, looking at normalization and normal forms. So today we're going to have a recap over normalization in a database management system. We'll have a look at the issues caused by data redundancy within a database system, and we'll look at how to remove redundancy and the inefficiencies related to that using normal forms and the decomposition of relationships into more efficient relations there. So to kick off, the concept of normalization is generally applied in order to remove redundancy from the database. It's a concept that relates to the design of databases, and we have to understand problems that can arise from having redundancy in a database design. There are several normal forms that have been proposed to actually help us with this, and essentially the higher a normal form is, the less redundancy there is in the actual relation. So a relvar is said to be in a particular normal form if it satisfies a set of constraints. So, for example, a relational variable that has lots of redundancy within it will be in a lower normal form than a relation that has a relatively small amount of redundancy in it. And we'll see how that's achieved and how to make relations, decompose them into more efficient configurations and into higher normal forms. So we'll start by considering our sample database. Here we have our MP and MP tables. They're the same database that we've been using all through this course to examine different concepts relating to database management systems. Now, what happens if we move the city attribute, which is currently in the manufacturer's table, if we move that into the MP table? So we end up with this relation MCP, and here we've got the MP table, but we've joined that to the M table to include the city attribute here. So we can see that every manufacturer M1 is in Sydney, every manufacturer M2 is in Brisbane, M3 in Brisbane, and M4 in Sydney. So we've got the same data, or effectively the same data, taken from the MP relation and the city column in the M relation, presented in a single table here. So what's wrong with this design? And the answer that we've got here is redundancy. So for every tuple for manufacturer 1 tells us that manufacturer 1 is located in Sydney. So that is, the fact that a given manufacturer is located in a given city is stated many times in the database there in this particular relation. And it's sort of a typical example of redundancy that we see in a database, that we can see in a database management system. It's worth noting that this redundancy is sometimes necessary in certain database systems or certain information systems. They may be a reason other than that sits outside the database that requires this particular piece of information to be stored in this table. But generally speaking, there are quite a few issues surrounding information redundancy, and that's why we have to have a system to design our databases so that they limit redundancy. So going through some of those issues, and we'll look at some very specific cases later on as well, but looking at some of the issues here, if we talk about updating the city for manufacturer M1. So say, for instance, we want to go from manufacturer M1 might be shown as being located in Sydney by one tuple. If we can update that in one tuple, we might put Darwin in another. So we end up with inconsistent data here. So the fact that a manufacturer is in a particular city is stored in multiple places in this design. So we see here we have multiple tuples with M1 in Sydney. If we change one of these to be Darwin, we'll end up with an inconsistent set of data within our database. In the case of the relational, so the subject of normalization, rather, is a formalization of this idea of removing redundancies. In the case of the relational model, relational values are always normalized. They're always said to be in first normal form, and this is because they contain atomic values. So each attribute has only one value stored in it. So hence we always say that a rel var is always normalized. It's always in first normal form. A given relational variable might be normalized in this sense, but it can still have our undesirable properties. So if we go back to our example here, we can see that there's only one value for every attribute within each tuple, so it's in first normal form. But because we have this redundancy within the city attribute, it's still quite undesirable. So the principles of further normalization allow us to detect these cases of redundancies and actually produce or decompose these relational variables down into more desirable forms. So as we've said before, a rel var is said to be in first normal form if it satisfies the condition that it contains atomic values, and as a result, every normalized rel var is in first normal form. It is possible to normalize into higher normal forms. So we've got second normal form, third normal form, and Boyce-Codd normal form. So E.F. Codd introduced the concept of the normalization procedure by which a rel var in a given normal form can be converted into a set, or decomposed into a set of relational variables, each of which is in a more desirable form. So the idea is we take this take a relation like this MCP relation and break it into a set of relations that are actually in the more desirable form. This process is called normalization, and it's fully reversible. So it's always possible to take the output of the procedure. So for example, if we were to break this example back down into the MP and the M table, you would be able to reverse the process by joining those back together to get back to this table. So it's always considered to be a reversible procedure, and you can convert them back into the input, so back into the lower normal form relational variable, because there's no information loss going on there. So if there's information loss going on, it means that we've done something wrong in our procedure. So the first three normal forms, first, second, and third normal form, were defined by E.F. Codd and all normalized. So going through these normal forms here, we can see that all normalized relational variables are in first normal form. Some first normal form rel vars are in second normal form, and some second normal form rel vars are also in third normal form. And as we go up the levels of normalization from first to third, we get to a more desirable configuration. So third normal form is more desirable than second normal form in terms of information redundancy. So as I mentioned before, we normalize our relational variables by breaking them down or decompose them using a reversible non-loss process. And this concept of decomposition or lossless decomposition is very closely related to the concept of functional dependency that we looked at in the previous lectures. So, for example, we've got a motivating example here for decomposition. So before we move on, remember functional dependencies refer to attributes within a relation determining the value of another relation, or to look at it the other way, having attributes in the relation that depend upon other attributes. So for example, we might have an attribute such as our product ID, and it determines all of the other attributes such as our P code, our product name, etc. Within each tuple. So they're all said, each of the other attributes are said to be functionally dependent on the product ID there. So we'll move on now with our example. So say for instance we have our rel var M, and it has the heading MID, status, and city. We'll ignore M name here. So we've got this relation here down the bottom to start with. Now we've got three attributes here, so it's possible to come up with two different configurations to actually decompose that particular relation. So we can see in the first one here, we've created the table MST, which has the MID and the status, and we've got MC, which has the MID and the city. So we can see we've broken this relational variable with three columns down into two relational variables that each have two. The second configuration here does the same again. It breaks this three attribute relation down into two tables. But here we've got the MID and the status, and then we've got the status and the city. So this is sort of an alternate configuration here. Now there's one of these that's desirable and one of them that is not so desirable because in the decomposition one of them has actually lost information. So if we move forward here, we can see in case A there's no information loss. The MST and MC MC tables or relations actually indicate that manufacturer M3 has a status of 30 and a city of Brisbane M5 has a status of 30 and a city of Melbourne. So we can see here, if we were to join those two relational variables together, we would get straight back, if we join them together by the MID, we'll get straight back to our original relational variable over here with M3 and M5 records with their respective values there. If we look at the second configuration here, we've actually had some information loss. We can still see that both manufacturers have a status of 30. So if we jump back here, we can see here that we've got both M3 and M5 have a status of 30. But because we haven't got the MID down here, we've actually lost the information regarding which city they're in. So if we were to join these two back together, the only common attribute we've got here is city. So if we join them together, we actually end up with a table. If you were to implement this in our Postgres database and do a join between these two, you'd actually end up with a resulting relvar that has 4 values with each different possible configuration there set up because we're not joining by a unique ID. As a result, we've had some information loss. So as I mentioned before, in case A, you can actually join them back together to get back to our original relational variable. In case B, we don't get back to our original relational variable. Hence, we haven't decomposed that in a correct way because we've had our information loss. So here we're looking at reversibility, and it means basically the original relvar is equal to the join of its projections, with each of these subtables here, the decomposed tables, being the projections there. So the idea is we want to be able to have a fully reversible system that allows us to decompose our relational variables down into more desirable forms. So here we've covered the concept of decomposition, but we'll move on with how this is actually used to reduce redundancy. So just before we move on here, we've got a little bit of theory. This is one of these annoying slides that has lots of symbols and letters and things on it. But if we've got a relation here, so we've got relation R with a relvar R with attributes or sets of attributes A, B, and C. If R satisfies the functional dependency A determining B, then R is equal to the join of the projections of A and B and A and C. So this is actually just a formal description of what we've just looked at in the previous example. If we look at A and B and A and C here, we can see that this is the same situation where A is our MID and B and C are our following attributes here because we've got A determining B. So it's just a formalization of the functional dependencies in there. So given the fact that, that we've got a relation that satisfies these functional dependencies, it's clear that M is equal to the join of these projections. So as I said before, in layperson's terms, when we join those two together, we get back to the original relational variable because MID is determining the city and the status there. Functional dependencies can be viewed as special types of integrity constraints. So the fact that in the M table, the functional dependency MID determines city means that each manufacturer is located in precisely one city. So if we go back to our original example of the MCP table here, if we change one of these attributes, so if we change Sydney here over to Darwin, we're then sort of voiding that integrity constraint there because the manufacturer 1 then effectively belongs to 2 different cities. And that's not a situation that we want to work with. Just a quick note down here in the final point. Presently, we're assuming that each relational variable has only one candidate key, which is assumed to be the primary key. So in all of these, when we're introducing this concept of normalization, we're just working with very simple relations that just have a very basic primary key. And we'll dig into composite primary keys in the second slideshow that deals with normalization and Boyce-Codd normal form. So moving forward, just to recap yet again, every relvar is in first normal form because every attribute contains only exactly one value. A rel-var is said to be in second normal form if and only if it's in first normal form, and every non-key attribute, i.e. an attribute that's not part of the primary key, is irreducibly dependent on the primary key. And here we're dealing with a simple situation where we've got a very simple primary key. A rel-var in third normal form is in third normal form if and only if it's in second normal form, and every non-key attribute, so every attribute not participating as part of the primary key, is non-transitively dependent on the primary key. So we'll cover this idea of transitivity as we move on here, but basically the idea is we want to get to a situation where the primary key is responsible for determining the values of all data in all of our tables. Ultimately, we want to be able to decompose every relation into a set of third normal form relations if they're not already in third normal form. So here's our informal explanation here. So a rel-var is in third normal form if and only if the non-key attributes are mutually independent. So you don't have this situation where non-key attributes are determining or dependent on the values of each other, and we'll see later on in some examples of where they are not mutually dependent and why that's an issue. And they need to be irreducibly dependent on the primary key. So we've used this term a couple of times, this irreducibly independent term. So what's meant by that? Basically, the attribute has to be determined by the primary key as a whole and not any part of the primary key if you're talking about a composite primary key. So for example, in MCP, our relation we looked at before, we've got the primary key, which is MID and PID, and it determines the city. But we also have this situation where the MID is determining the city because each manufacturer only exists in one city. So the city is also functionally dependent on the MID alone, not the entirety, not the MID-PID primary key combination. So here we can see that the functional dependency MID determining city is left irreducible. We say that that it's irreducibly dependent on the MID, but not irreducibly dependent on MID-PID, because we can see we can break this dependency down further based upon the manufacturer ID there. So we can see here that because we have this cross dependency with MID determining city, that it's not irreducibly dependent on the complete primary key. So to go the other way, we can see that the relation P, so our products table, is in third normal form. And that's because all of the non-key attributes, so our P code, our P color, weight and city, are all independent of each other. They can all vary completely independent. So you can have a P code of X, color of Y, weight of Z, and a city of A. And then the next record can have a completely different configurations of value. There's no single one of these attributes here determines the value of any other attributes. Only the primary key, the PID, determines that. So therefore, we can see that all non-key attributes are said to be irreducibly dependent on the primary key. And this is evident from this set of functional dependencies down the bottom here, where we have the primary key determining the value of every attribute. So they can vary completely independent of each other, only being determined by the primary key. So when we have a rel-var in first normal form and not in second normal form, and hence not in third normal form, it might actually still have an undesirable structure. So let us suppose, I've got some examples here. So let's suppose we have, instead of splitting the rel-vars M and P, we actually combine them together into a relational variable called 1. Now again, we cut out the manufacturer name here for simplicity. So the result is that we end up with this relation down the bottom here where we have MID, city status, we have the PID and the quantity in there, and our primary key is MID, PID. So essentially what we're doing here is we're actually taking the MP table and combining the manufacturer status and city into there. So it's kind of like an expanded version of what we looked at with our MCP table. So if we look at our data here, this is the resulting relation over here. We can see we've got our MID, PID, city and status. And this diagram to the right here actually summarises the functional dependencies. So here we've got MID and PID as a whole, which is the primary key determining the quantity. And then we've got the MID alone determining the status and the city also determines the status. So we can see here straight away that some of these attributes, notably the city and the status, are not going to be irreducibly dependent on the primary key because they're dependent on the MID. So in the case of third normal form, the diagram shows arrows coming out of the candidate key, the primary key only, whereas a non-third normal form diagram has arrows out of the candidate key together, where together with certain additional arrows. So RelVar1 violates conditions A and B. So we have non-key attributes that are not all mutually independent. So here we can see that we've got city determining status. So they're not mutually independent. All of these attributes are not determined by the primary key. And we can see that they're not irreducibly dependent on the primary key because we've got this arrow coming out of this component of the primary key, not the primary key as a whole. So we can see here that this particular relation is not in third normal form. So if we look at this relation, we've got some problems concerning the different operations that you can perform on our database here. So first of all, we're going to have a quick look at what happens when you go to perform an insert on this statement. So here we've got a situation where you can't actually insert that a particular manufacturer is in a particular city until that manufacturer supplies at least one product. Now, that situation occurs because PID is part of the primary key. So for example, if we wanted to insert the fact that the city of Darwin had a status of 20 or a status of 50, for example, to be different, we couldn't do that because if there's but it doesn't supply any products, but we couldn't insert that record here because we need to have the PID because it's part of the primary key. So we can't insert a null PID because we can't have nulls as part of our primary key. So you can see that this structure isn't very desirable because we can't actually store that piece of information. So for example here, the table does not show that M5 is in Melbourne because M5 has not supplied any products. Because here we've got MID and PID as the primary key, and because of the entity integrity rule, the primary key can't accept any null values. So if we were to try to put, for example, if we wanted to insert MID of 5, status and city of Melbourne and 30 or whatever, and then we inserted null and null, that wouldn't be allowed because we would void our entity integrity rule because PID is part of the primary key. If we move on to the next operation here, we've got our delete operation. So here, if we delete we delete a tuple for which manufacturer only supplies one product, then we not only destroy the shipment information, but we also destroy the information about the city. So jumping back to our particular example here, we can see here we don't actually have any. We've got M3. M3 only has one record. So if we delete this particular record here, we'll actually run out. We actually won't have this particular information about this manufacturer in our database anymore. So we're not just deleting the shipment information, we're also removing the actual city information as well. And that's not really desirable because we don't want to destroy unnecessary information unnecessarily. The final one we're going to look at here is our problems concerning the update query. So if the city, for example, the city value for a given manufacturer appears many times in one. So here we go, here we've got manufacturer M1. If we go back to our table here, we can see that we've got several records that have M1 as the manufacturer, but we actually don't, and we have the information about the status and the city stored multiple times. So when we go to do an update, we have to update multiple records. So for example, if we go through an update, M1 moves from, so we update Sydney to Darwin, so M1 moves from Sydney to Darwin. Then we have either a problem of searching the relation 1 for every tuple connecting M1 and Sydney, and you have to change it. And then we introduced the possibility of producing inconsistent data, where some values for M1 might have Darwin and some have Sydney as the city. And it's a similar situation that we looked at right back at the start of this lecture in our original example with the MCP relation there. So again, we introduce the possibility of inconsistency there with our update operations. So how do we get around this situation? How do we actually improve the design of our database? So one solution is to replace this one rel var by actually splitting it into two relational variables. So here we've got the first one of these relational variables, and we've actually split that down into basically what is our MP table. So here we have MID and PID together as the primary key and quantity. So MID and PID determine the quantity, and then we've split into this, we've created this other relation here that we're calling 2. In this situation we have MID, which is our primary key, and we have our status and our city. So this has improved things a bit. So we can see here that this relation is actually in third normal form here, because we can see we've got one attribute, one non-key attribute, which is quantity, and it's determined by the primary key, which is the composite of these. So it's going to be in third normal form. Now, with this particular relation, it's still got a couple of problems here. We can see here that we've got MID determining both city and status, but the problem is we've still got this little functional dependency here. We've got city determining the status. So again, it's not going to be in third normal form because not every non-key attribute is not mutually independent of each other. So it's not going to be in third normal form. So we'll see in the next lecture, if you go through and review lecture 18, you'll see that you can actually break this down into 3 relational variables and get a much more efficient result where all 3 of them are in third normal form. But that's actually covered in next lecture. So go through lecture 18 to finish off looking at this particular topic. So today's slideshow was a bit longer than usual, but it covered off on some really important stuff. So we've looked at what normalization is and the issues surrounding redundancy in a database system. We've had a look at some of the different normal forms and how to actually decompose relations in a non-loss fashion into a set of more desirable relations that are easier to work with. So the important things to take away from this one are the issues relating to redundancy. So for example, some of the different the impacts on the different operations that occur in poorly formatted or poorly designed database tables, and just the concept of redundancy, what it is, and why it's bad. So keep working through, so we're covering off, keep working through chapter 12, finish reading that one up if you haven't already done so, and keep reading through keep working through assignment 2 and assignment 3. So this information on normalization from lectures 17 and 18 is very relevant for assignment 3 for the Comp 589 students, because you've been given a database table or a relation that contains a heap of data, and you've actually got to examine and analyze that data and break it down into a set of third normal form relational variables and actually implement that database. So make sure you have a good understanding of the concepts of normalization so that you can do that. So thanks guys, and we'll move on with the topics. With this week we're moving on to query optimization, and that lecture should be available for you tomorrow.